Part 3 of Unit 13 is about buffers. A buffer is a solution that pairs a weak acid and its conjugate base, or a weak base and its conjugate acid together. Buffers are designed to resist changes in pH even when strong acid or strong base is added to them. So some examples of substances that could create buffers, well, acetic acid is a weak acid, and if we made a solution of acetic acid and say sodium acetate, we've got a weak acid and its conjugate base here. That could create a buffer that resists changes in pH. Another example, hydrofluoric acid. It's a weak acid. If we make a solution of hydrofluoric acid and lithium fluoride, we have a weak acid and its conjugate base. That's going to make a buffer solution that resists changes to pH. So let's consider a buffer that's made with 0.1 molar hydrofluoric acid and 0.1 molar sodium fluoride. If we add base to that buffer solution, the base is going to react with the hydrofluoric acid. So we'd get HF reacting with the base to produce some fluoride and water. If we add acid to that solution, it's going to react with the conjugate base that was already present. So our fluoride ion was already there. If we add some acid to it, just using hydronium for a generic strong acid, we're going to end up with some of the weak acid hydrofluoric acid in water. So a buffer resists changes in pH when you add acid or base to it, because there's something different for the acid and base to each react with already there. This is one of the most important equations you're going to learn this year. It's called the HendersonHasselbalch Equation. It's our lifesaver equation for dealing with buffers. The Henderson-Hasselbalch equation is pH is equal to pKa plus the log of the conjugate base concentration divided by the weak acid concentration. Another way you'll see that written is A minus for a generic conjugate base and HA for a generic weak acid. That's how it's written for an acid and a conjugate base. We actually have another form of the Henderson-Hasselbalch equation for if we use a weak base and its conjugate acid. POH is equal to pKb plus the log of the conjugate acid HB plus over the concentration, forgot my concentration symbol, over the concentration of the base. So only this top form is given to you on the green sheet, the acid form, but the base form is not hard to figure out from that. The Henderson-Hasselbalch equation helps us figure out what a new pH of a buffer solution will be when we make changes to the conjugate base or acid concentrations at equilibrium. If you remember back in 13.1, we talked about the half equivalence point, and we said that the pH at the half equivalence point was equal to the pKa. Well, the reason why is at the half equivalence point, the concentration of the conjugate base and of a weak acid are the same. So if I was just going to use 0.5, I'd have 0.5 divided by 0.5, taking the log of it. Well, the log of 1 is 0. So at the half equivalence point, pH is just equal to the pKa. That's where that trait about the half equivalence point came from. So if we look at a question involving the Henderson-Hasselbalch equation, what is the pH of a buffer that is 0.12 molar in lactic acid and 0.1 molar in sodium lactate, and they give us Ka for lactic acid? Well, we've got our equation. pH is equal to pKa plus the log of the conjugate base concentration divided by the weak acid concentration. Well, we've already got all this information, we just need to plug it in. So pH is equal to the negative log of our Ka value, 1.4 times 10 to the negative fourth, plus the log of our conjugate base, that's going to be the sodium lactate. Usually sodium and potassium are used as cations in this situation, and that's because most of the time they're spectators. We're interested in the anion that's going to be the conjugate base for the weak acid. So it's 0.10 in that divided by 0.12, the weak acid concentration. Well, you just have to plug all that into a calculator, and you end up with 3.853 plus a negative 0.079. You end up with the pH being equal to 3.77. Buffer solutions, unfortunately, don't resist changes in pH from 1 to 14. They work over a specific range. When you're creating a buffer solution, we need to choose an acid that has a pKa value close to the pH we're trying to maintain. The point of a buffer system is to resist changes in pH, maintain a constant pH. So to make an effective buffer, we need to choose an acid that has a pKa value close to the pH you're wanting to maintain. So once we have a buffer made, we're going to add strong acid or strong base to it to try and change the pH. When strong acids or bases are added to a buffer, it's safe to assume that all of the strong acid or base is used up in the reaction. What we need to do from there is determine how the neutralization reaction affects the amounts of the weak acid and its conjugate base that are in the solution, and then use those new values in the Henderson-Hasselbalch equation to determine the new pH of the solution. So here's a pH change in buffers question. A buffer is made by adding 0.3 moles of acetic acid and 0.3 moles of sodium acetate to enough water to make 1 liter of solution. So 0.3 molar acetic acid and 0.3 molar sodium acetate. We need to calculate the pH of this solution after 0.02 moles of sodium hydroxide is added. We're going to assume no change in volume. When you do have to take into account volume change, it's going to be a significant amount. They'll tell you how much was added, or they'll say volumes are additive. But in this case, they're just telling us 0.02 moles of sodium hydroxide, so we can assume the volume stays the same. They've given us the Ka of acetic acid. In the pH of our buffer before we added the sodium hydroxide is 4.74. Well, before we can go to the Henderson-Hasselbalch equation, we're going to have to set up a rice table to figure out changes in our weak acid or conjugate base concentrations. Well, since we're adding strong base to our buffer, it's going to react with the weak acid that's present. So my reaction for this rice table is the weak acid plus the sodium hydroxide. Sodium is a spectator, so I'm just going to call it hydroxide. And that's going to produce my conjugate base, acetate, and water. My initial concentrations, it was 0.3 for the parts of my buffer, and they told me that we're adding 0.02 moles of sodium hydroxide. We can assume that all of the sodium hydroxide reacts, so it's minus 0.02, so there's none of that left over at equilibrium. It's going to be minus 0.02 for the acetic acid, so at equilibrium it's 0.28. And the conjugate base, the acetate, that's actually a product in this dissociation reaction. So it's going to be a plus 0.02. So at equilibrium, there's going to be 0.32 moles of the acetate present. Now that we have the new equilibrium concentrations after adding the strong base, now we can go back to the Henderson-Hasselbalch equation to figure out the new pH. So we're going to plug it in as pH is equal to pKa plus the log of my conjugate base concentration, 0.32, divided by the weak acid concentration, 0.28. So when you simplify that, the negative log of the Ka value is 4.745. This is 0.058. So my new pH is 4.8. Your question for this section: calculate the pH of a buffer that is prepared by adding 0.15 moles of sodium nitrite to 1 liter of 0.25 molar nitrous acid.